Welcome everyone to the third day morning session. Today now we have Nick Mavromatos from King's College London, and he's going to talk about gravitational anomalies in string-inspired cosmology, primordial gravitational wave condensate, and spontaneous Lorentz symmetry breaking, from dynamical inflation to matter-antimatter asymmetry. So please, Nick, go ahead. I will let you know after 10 minutes.
Thank you, Francisco. Thank you, Jorge, for your kind invitation to this very nice conference, which I'm enjoying. Happy New Year to everybody. What I'm going to discuss today, following the spirit of the conference, I'm going to outline first the parts and then the whole. The parts I've outlined, the parts of my research I've outlined in these little notes, and center stage is occupied by the so-called dark energy of the running vacuum model type, RVM, which you have heard on Monday in the talk by Joan Solà. Another crucial role will be played by stringy gravitational actions, the so-called model-independent actions in string spectrum, which are connected to torsion, and they are also intimately linked with gravitational anomalies. The latter themselves are linked with primordial gravitational waves, in the sense that in a Robertson-Walker space-time, gravitational anomalies are absent unless you have perturbations of gravitational wave type, which violate CP. We can discuss the formation of anomaly condensates, which lead in turn to spontaneous Lorentz violation, and then dynamical inflation without external inflatons, which is of the type encountered in the running vacuum model or RVM approach to cosmology. This spontaneous Lorentz violation will also lead, during the radiation era, to Lorentz violating leptogenesis and eventually matter-antimatter asymmetry in theories which include right-handed neutrinos, and the corresponding Lagrangians resemble that of the standard model extension effective field theories, where the CPT and Lorentz violating terms are due to this anomaly condensate. In this sense, in the sense that I can generate matter-antimatter asymmetry from gravitational anomalies, we can say, if you like, that we exist because of anomalies. That's the anomalies are good things in my approach. Finally, the initially massless gravitational actions can acquire masses during the matter era as a result of non-perturbative effects, and in this sense, they could play the role of dark matter. And since they are connected to torsion, as I will discuss, we may have a geometric origin of dark matter. Finally, in the current era, the dark energy acquires again an RVM vacuum model type form, and as was discussed on Monday by Joan Solà, this has important phenomenological implications that distinguishes the model from lambda CDM. So what is the whole? Well, you probably suspected what the whole is once you have the task to explain the universe. Of course, the whole is the real theory of quantum gravity, which we don't know actually what it is. So allow me to only discuss a partial whole, if you like. In other words, I will try to discuss an effective field theory of the universe that connects smoothly all the above phases. And a very good candidate for this is the running vacuum model of cosmology, which, however, I will embed in string theory. There is an important variant of RVM model where anomalies will play a crucial role, and string theory is viewed for me as a microscopic quantum gravity model. So in this talk, I will first give the Lagrangian for this stringy model of RVM, which was developed in collaboration with Spyros Vassilakos and Joan Solà. And then I will link it with spontaneous Lorentz violation through appropriate gravitational action backgrounds and matter-antimatter asymmetry in theories with right-handed neutrinos. And this is a program that I'm doing in collaboration with Sab and Sarkar, Marco De Cesare, and my ex-PhD student, Thomas Bossinger. So let me discuss some of the parts in detail, starting from the gravitational actions. As you know, this is a well-known topic in string theory, the gravitational or model-independent actions that exist in any string theory. I've associated with the spin 1 and the symmetric rank tensor of the Kalb-Ramond field of the massless gravitational multiplet of strings. The other two members of that multiplet is the dilaton and the graviton. Due to a U1 gauge symmetry of the antisymmetric tensor field, it appears in the effective action only through its field strength. And in the presence of anomalies, the field strength is no longer given simply by the curl of beta, but it is augmented by the Chern-Simons terms, which are related to gravitational anomalies. Omega is the spin connection, or to gauge anomalies. A are gauge fields, non-abelian gauge fields in general. These terms are related to the so-called Green-Schwarz counter terms. They will play an important role. In our case, we will not cancel the anomalies. The torsion role of the H field can be understood by absorbing the h square terms in a generalized scalar curvature when you combine them with a Hilbert action. And this generalized scalar curvature contains a generalized connection, which is not symmetric in its lower indices, and it contains a torsion, which is proportional to the H field. Throughout my discussion, the dilaton will be set to a constant. You can quantize this torsion, and indeed you can show that this quantization results in a gravitational action degree of freedom, B, the B field, the carbon field, which is dual to the H torsion. And the action acquires this form. I don't have the time to go through in details. The important point is that this gravitational action, which classically is connected to the torsion by this relation down here, in other words, its derivative is proportional to the torsion, this field couples with the anomalies due to the Chern-Simons terms in the definition of the H, and also its derivative couples to the axial current, which involves all currents, all species of fermions, because the coupling is universal. I stress again that these coefficients that you see here, alpha prime is the inverse of the square of the string scale, which is different from the gravitational Planck constant. All these constants are valid in when you embed the theory in string theory. In a generic theory with anomalies, you cannot determine those coefficients. So this is our model. This is the Lagrangian that we are going to use to describe the whole that connects smoothly the various phases of this universe. And we are going to discuss backgrounds of Robertson worker where this quantity vanishes. Let me now go to the anomalies and discuss some features. In contrast to the topological nature of the gauge anomalies, the gravitational anomalies, the tilde here denotes the dual of the corresponding tensors, spoil the conservation of the stress tensor. Why? Because its variation with respect to the method gives rise to the so-called cotton tensor, a traceless tensor, which contributes actually negative contributions to the vacuum energy density, as we shall show later on. In the presence of this cotton tensor, Einstein's equation is modified. For us, the matter here is, the word matter is in a generalized sense because this is the gravitational action belonging to the multiplet of this massless multiplet of the string. But the important point is that this tensor is not conserved. It's proportional to the anomaly and the derivatives of the action. This term, by the way, R tilde alone is a total derivative for a constant action. That's why you get zero when the action is constant. And this spoils the conservation of the stress tensor of matter. But there is no problem with general covariance because you can always put this stress tensor in the definition, you can absorb it in the definition of the matter stress tensor, define a modified stress tensor, and simply the presence of the stress tensor of the cotton tensor indicates the exchange of energy between gravitational actions and gravity. And there is no problem with diffeomorphism values. Let me now see what's the role of primordial gravitational waves in anomalies. The important assumption we made in our approach is that the model for the early universe comprises only of gravitational degrees of freedom from the multiplet as external fields. Matter is generated at the end of inflation, as we shall discuss. So, assuming constant dilaton, we have only gravitons and axions and gravitons. If you do not have gravitational waves, because the axions have no potential in string theory, you get a stiff axion matter with the equation of state W plus 1 in early phases, in pre-inflationary phases. I remind you here the model of Zeldovich, who again foresaw a stiff matter, but for Zeldovich, the stiff matter comprised of baryons rather than axions, as in our case. Now, in the presence of primordial gravitational waves, this term is not zero. Now, what is the origin of these waves? We have discussed in our review with solar potential origins, which I will not go through in detail because of lack of time. But I mentioned, first of all, that this might be due to primordial black holes formed from collapse of massive defects. We have heard on Monday from Garcia Bellido that primordial black holes may be formed out of ordinary matter. Here, I'm only considering massive gravitational stringy defects because I don't have matter in the early universe. Moreover, another way to form gravitational waves is from the collapse or collisions of domain walls formed in theories with approximate discrete symmetry breaking. And for instance, you may have a bias in double well potential of some condensates, like gravitino condensate. You may have a break of degeneracy here. In our approach, for instance, it is this phase, if you consider such models, that the RVM inflation will be induced, and the condensate here is stabilized. So let me proceed now to see if you have gravitational waves, independent of what is the precise origin, how you can get non-trivial contributions, how you can get condensates of anomalies, spontaneous Lorentz violation, dynamical inflation of RVM type. First of all, if you have a condensate of anomalies, you can split the gravitational Chern-Simons interaction. Remember that I have no gauge fields here in our model because only gravitational degrees of freedom are present. So this term contains the anomaly terms, and these are the quantum fluctuations. This is like a mean field approach, if you like. The mean field, at mean field level, i.e. the condensate itself, will contribute a cosmological constant-like term, which will dominate inflationary phases.
Let's see now. You have 5 minutes remaining. 5 minutes.
Yes,
5 minutes.
Sure, thank you. That's more than. So, first of all, what I do is I start from the anomalies I consider in total derivatives. I, first of all, assume an inflation. I average over inflationary space-time using gravitational waves, but then I use anisotropy and homogeneity of the universe to write the anomaly equation in this form. I use the action equation of motion in the presence of anomaly, which allows for a solution which is such that the time derivative of the Kalb-Ramond action is proportional to the temporal derivative of the anomaly. Then I write down the anomaly equations. I put a cutoff for the graviton modes, and I end up in this expression, which in general, this coefficient is non-zero, is positive, and would imply an exponential decay of the anomaly at the end of inflation. But if you fine-tune the string scale and the ultraviolet cutoff to this quantity, you can end up with this coefficient vanishing, and therefore a constant term for the anomaly. Taking into account Planck data that this is of order 10 to the 4, you can ensure constant anomaly if the string scale is 3 orders of magnitude less than the ultraviolet cutoff, and you can arrange for sub-Planckian string scale so as the ultraviolet cutoff does not exceed the Planck scale, so you don't have trans-Planckian modes. This constant B dot that you ensure in this solution violates Lorentz because it corresponds to a constant torsion, and Planck data implies that the slow roll parameter here is, and this term leads to a total energy density comprising of contribution from the action, Chern-Simons term, and condensate, which acquires the standard RVM form in the sense that it is proportional to even powers of the Hubble parameter. This parameter is dominant in the early universe and drives inflation, and you can apply the RVM dynamics as explained by Joan Sola to indeed now recover in a self-consistent way the de Sitter solution for the the time evolution of the rho total. And I stress again that the slow roll is played by this Kalb-Ramond action. The only difference from RVM is that this coefficient is negative due to the negative contributions of the Chern-Simons term to the energy density. Now, the important upshot of this is that at the end of inflation, you have an undiluted Kalb-Ramond background, which now brings me to the last topic of my talk, why this is important for leptogenesis in the matter era. Actually, in the actual model, you have a generation of chiral fermionic matter at the end of inflation, which in turn generates anomalies on its own because the chiral axial current is not conserved. And this cancels the gravitational anomalies due to the Green-Schwarz counter terms. So this cancellation allows for chiral anomalies to exist, possibly also of QCD type, FF dual, where F is the gluon tensor during the radiation era. And this implies simply that the B dot is not constant, but varies with temperature like this. Nevertheless, this is qualitatively similar to approximately constant background, as we've shown here in collaboration with Bossingham and Sarkar. And now I'm going to explain briefly how massive right-handed neutrinos can lead to this. First of all, I assume this is the action for massive neutrinos. This is the right-handed neutrino field. I didn't specify the origin of the mass of the right-handed neutrino here, but I can say that it may be generated due to non-perturbative effects that break shift symmetry, as we might hear from the next talk by Alex Soto. For us, I include an approximately constant background in this action, which means that this action resembles a standard model extension with CBT and Lorentz violating term due to this anomaly term. And the portal, which connects the neutrinos with the doublets, the SU2 doublets and the Higgs sector, here because I am above the electroweak symmetry breaking, all the Higgses, including the charged ones, are present. So this leads to anomalies in the sense that the decays of the right-handed neutrino to standard model leptons and antileptons are not the same in the presence of the anomaly. This means that there is a lepton number asymmetry at the end at 3 level, in contrast to the standard CPT conserving CP violating term, which requires loops. You can evaluate the lepton asymmetry following a standard Boltzmann approach, and you find it to be proportional to this ratio. You fix this ratio by insisting on the phenomenological value of the lepton asymmetry, and actually to be consistent via seesaw mechanism with light neutrino masses in this model and the stability of the Higgs vacuum. These are the numbers that you can take easily. The decoupling temperature can be saturated by the mass of the right Honey neutrino. And I also stress that these approximate numbers are also valid in the actual situation where the B0 is not constant but varies with the temperature as each cubic power. Then biogenesis is done in the standard way. I don't have the time to explain it. The lepton number the asymmetry is transported to the baryon sector through B minus L conserved Schwarzschild interaction. Finally, this is my last transparencies, if you like. That's the whole. The whole is the evolution, which we have discussed so far. We started from an RVM inflationary phase, which was induced by primordial gravitational wave condensate. We ended up with a Lorentz violating background for actions, which indeed was responsible through the generation of chiral matter and the cancellation of the gravitational anomalies during the radiation era for leptogenesis in a CPT violation way. So anomalies play a central role. I don't have the time to discuss the matter era, but the massless actions can acquire masses through instanton effects during the QCD era. And in our model, where only gravitational actions are taken into account, the masses that we found following these constraints on the string scale to be in the region to allow for this Lorentz violating solution are 10 to the minus 5, between 10 to the minus 5 and 10 to the minus 11 eV. This action, if we place the role of the dominant species of dark matter, because it's associated with torsion, leads to a geometrical origin of dark matter, if you like. But of course, it's true here you have other actions, and you can discuss mixing of the other actions with these gravitational actions. These other actions depend on details of compactification, and you get a much more recent, rich phenomenology. The modern era is still something we're working on. That's my last word. Because the universe enters at the center of space, the gravitational anomalies resurface, but still you can assume a slowly moving Kalb-Ramond backgrounds. Because this is torsion, you need to get consistent solutions with the torsion constraints from Lorentz violation and CPTV. You do that if you assume, and also you can also get the order of magnitude of the dark energy and dark matter predicted by the CMB data. And for this, you require this equality, approximate equality of the slow error parameters today with the slow error parameter at inflation. Using this assumption, you can scale back without temperature dependence to the inflationary era smoothly, this quantity. But this is an issue, why we have another coincidence limit, if you like, why phenomenology requires that the epsilon prime today is the same as the epsilon at inflation. This needs to be better understood. I will not say anything on the RVM type today. I will only point out that this is a positive coefficient, which in order to fit the data is over the 10 to the minus 3. And this varies with the Hubble parameter as the square of the Hubble parameter. And as you heard from Joan Solà, this has important phenomenological implications and distinguishes the model from the lambda CDM and could alleviate tensions. So let me conclude with a nice picture here where, if you like, the various white parts could be viewed as representing the windows of the Casa del Todo. I put in the oculus of the Casa or in the caldera of the volcano, if you like, the gravitational anomaly, because it connects Lorentz violating backgrounds through the matter and the matter dominance, and that's why it explains why we exist. So we may be paraphrasing Carl Sagan, who was saying that we are made of stardust. I would say we are made, we anomalously made of stardust. Thank you very much for your attention.
So thank you very much, Nick. Let's thank Nick. Thank you. I think we have time for one question. And please, Alfredo Iorio, you have a question. Go ahead.
Thank you, Francisco. Nick, fantastic talk as usual.
Thank you, Alfredo.
Unfortunately, well, I don't know how much unfortunately, but I cannot show it myself because
I see your picture, which is okay.
Okay, but it's me. It's me. I hope you recognize.
Yes.
Listen, I'm very much fascinated by the role of torsion in your thing.
Yes.
So I saw that torsion sometimes is there without the spinner, sometimes it's with the spinners. I understood that this is crucial for having your anomaly. But sometimes I saw in the formula that the gravitational tensors like the Riemann curvature and so on and so forth had no torsion in it, and sometimes they have it. Can
Yes.
you because sometimes the field B was present.
That's right.
And so it's that sort of dynamical, and some of the time it becomes a sort of background. Can you just tell me a bit more on this? It is
Yes.
very fascinating.
I can be very brief now, and we can discuss later. Actually, for us, you could forget about torsion in the sense that you can have your graviton plus this field B. It's dynamical. However, you can always absorb it as long as you are interested in the lowest order Lagrangian. You can always, let me show it here if I can share again. Sorry, here. So can you see my transparencies?
I do. Yeah, I can.
Okay, good. So what you can do is with the torsion is the following here. Here is an independent field in string theory. It is that field, all right? That's your action. Right. This is the torsion-free component of the curvature. However, you can absorb R and H square and up to order alpha prime in a generalized scalar curvature with a torsion.
How? You put
you can
equation of motion.
In other words, you can use the Bianchi identities. This field vanishes. If you concentrate it only here, the antisymmetric derivative is 0, and that's how you don't have the kinetic terms.
So it's not a question of motion. It's a Bianchi identity.
It's not an equation of motion. It's a Bianchi identity precisely. And eventually, I use it when you dualize it again using the Bianchi identity. You arrive at no torsion, but the only remnant of torsion is this B field. So essentially, you start from the H square term. You substitute this classical equation. You see the torsion doesn't propagate to lowest order. It doesn't have derivatives of H. Orders it propagates and you get corrections. So in the dual version, you don't have a torsion. That's your question essentially. But the remnant of torsion is the action. So in a sense, the action corresponds to a pseudoscalar field. The torsion corresponds to a pseudoscalar field in this formalism. It is interesting if you try to do it with Einstein-Cartan without reference to strings, then you see that then there are some problems, but which I'm happy to discuss.
Okay, thank you very much.
No problem. There was one other question, but I can discuss them in the chat.
Thank you very much. Yes, sorry. I think that we are
no, that's fine. I can
on time. Let's thank. Yes, let's thank Nick again. Thank you very much, Nick.
Thank you.